Hello, you're welcome to MasterTMathsclass. And here in this live class, we want to look at circle geometry. So we are looking at a topic, circle geometry. Then we have some circle theorem that we look at the first one in our previous class, which states that the angle at the center of a circle is 2 times the angle at the circumference. So when we have a circle which is having the center hole like this, the angle formed by a chord, let's say this is chord AB, the angle formed by this chord, or it might be an arc, so we might use an arc AB, the angle formed by the center here, which is this obtuse angle here, then is equals to 2 times angle formed at any part of the circumference. So let's call this point C. So this angle here is angle at the circumference. So angle at the center is twice the angle at circumference. Now, if the angle at circumference is x, angle at center here is now 2x. So that's the first theorem. And we also have the second part of the theorem. That is, if we have the center here, then we have the chord AB given a chord or an arc, angle formed at the center here. In this case, we consider this reflex angle at the center. So angle formed at the center here is twice the angle formed at the circumference on the other side here. So which means this angle is at the circumference here. So this angle, if it is y here, so this angle at the center here is 2y. So we looked at the proof of that theorem in our last live class. So endeavor to check to see how this theorem is being proved. And also another theorem follow this, which will be theorem number 2 from this class. And the theorem number 2 here, we have angle formed in the same segment by a chord are all equal. Now let's look at this circle here, then and look at a chord of a circle. So given this circle here, which is having center hole here, then let's say we have a chord. Let's call this chord AB. Now this chord has divided this circle into 2 parts, that is 2 segments. So here we have the major segment here and we have the minor segment. Now all the angle formed by this chord in one segment are all equal. So let's say this angle here is formed by this chord in this major segment. So we have another angle formed also by the chord in this segment. Also we have it this way formed at this part of the circle. So we form this angle. So we have this angle, and this angle. Also, we can form another one, as many as possible, by this same chord. And sometimes we might not have a chord, it might be an arc. So when we have arc AB, it's still, applicable to that. Then all the angle formed in one segment like this are all equal. So that's the theorem. This follows from the proof of the first theorem. That is, we can connect from construction, join A to the center, also B to the center. And when we look at this angle here, this obtuse angle here, angle at the center, we can see that is serving as angle at the center to the angle at the circumference here. So when we pick just one angle here, following this, so if this angle is x, angle at the center here will be 2x. Now, this is angle at center, which is 2x. So each of these angle as well is angle at the circumference. That is, angle at center is twice the angle at circumference. So if it is 2x, this is also expected to be x. Also, this is also expected to be x. This is also expected to be x, because angle at center is twice the angle at circumference. Now, hence, we can see here that angle in the same segment are all equal. So the second part of it as well, it might be in the minor segment. So we have this center, we have this chord AB, and this angle might be formed in the minor segment by this chord. So we have this angle. Also, we have this angle formed. Also, we have this angle, it might be as many as possible. So all these angle here are said to be equal. So that's angle in the same segment. Now, we also have theorem number 3 here, which is equally important. And when we have a circle, center O like this, and we have a line that passes through the center, this line that passes through the center is same thing as diameter. And diameter here divide the circle into 2 equal parts. So we have a semicircle now. So angle formed by this diameter, let's call it AB. So it's same thing as angle formed in a semicircle. And this angle here now is angle 90 degrees. So it implies that angle in a semicircle is 90 degrees. The proof also follows from the first theorem here. That is, when we look at this center here is a straight, is a straight angle now. That means 180 degrees. So this angle at center is 180 degrees. And angle at center is 2 times the angle at circumference. So angle at circumference, of course, will now be 90, because that will be 180 degrees over 2, which is 90 degrees. So this particular theorem as well is very important in circle theorem. Then we also have another theorem here, which is equally important. We have a line drawn from the center of a circle to the midpoint of a chord is perpendicular to the chord. So let's see from here, when we have a circle at center O, then we have a chord AB. Now, a line that is drawn from the center of this circle to this chord here, it meets at angle 90 degrees with the chord, and also bisect this chord. So when we label this as N, then it implies that line AN is now equals to line BN. So the line will divide this chord into 2 equal parts and also meet at angle 90 degrees. That's a particular theorem as well. So, and when we complete this diagram, from the center to the circumference here, we are going to have a radius R. So also from here is also a radius, which make it, when we bring this out, we have 2 right angle triangle which are similar here. Then if any side is missing, we can easily find it. Sometimes we'll be given the length of the chord, and if the length of the chord is given, then the radius is given. By this line, the length of the chord we divided into 2. So if the length of the chord, for instance, is 10, it means from A to N will now be 5, from B to N also will be 5. Then if the radius here is 4, or let's say the radius here is 5 and this is 8, so this is 4, 4. So 5, 4, then we can get the distance from the center to the chord now, applying Pythagoras theorem. And from Pythagoras triple, hypotenuse is 5, one of the side is 4, so the other one will be 3. So which is 3, 4, 5. Now, so that is that. One particular theorem as well. Now, let's look at a question here. A chord is 10 centimeters from the center of a circle. Example on this. A chord is 10 centimeters from the center of a circle of radius 12 centimeters Calculate the length of the chord. Calculate the length of the chord. Now, when we interpret this question in diagrams, we can have the circle, which has a center. Then we are given a chord. A chord is 10 centimeters from the center. So let's say we have the chord AB. And this chord here is 10 centimeters from the center. So the distance between the center and the chord now means we have 10 centimeters. Then radius of the circle here, when we join the center to the circumference, is radius. So the radius here is 12 centimeters, which is equally from here to here, 12 centimeters. And don't forget, this meets at angle 90 degrees. Then we have to find the length of the chord. And the length of the chord means AB. So let's label this as N. And when we bring out triangle AON, this is triangle AON, which is a right angle triangle there. So we have AON. This ON is 10 centimeters, and this AO is 12 centimeters. Then we can find AN. If you let AN be x, from Pythagoras theorem, that means x squared will now be equals to 12 squared minus 10 squared, because here the hypotenuse is 12. So that here we have x squared is now equals to 144 minus 100, which implies x squared equals to 44. Then taking the square roots on both sides, we have x is now equals to square root of 44. And with your calculator, we can get this to 2 decimal places at 6.63 centimeters. That's just AN, which is the half of the chord you are finding. Now, therefore, you can say chord AB now will be equals to 2 times x, which is 2 times 6.63 centimeters, which gives us 13.26 centimeters. So hence here, the length of this chord is 13.26 centimeters. So this is one of the questions here applicable to that given theorem. You are watching us live at MasterTMathsclass. Do well to give a thumbs up and share this video. Also subscribe in order not to miss out on our videos. Now, here also we have another theorem, and which is on cyclic quadrilateral. So, and what did they mean by cyclic quadrilateral? A cyclic quadrilateral is a quadrilateral that is inscribed in a circle. Just as the name implies, cyclic quadrilateral. So when we inscribed a quadrilateral inside a circle, that implies that we have what is called a cyclic quadrilateral. Now, when we have a circle like this, and we have a quadrilateral that has its 4 angles touching the circumference. So here, since a quadrilateral has 4 angles, so its 4 angles is touching the circumference of the circle, We have 1, 2, 3, 4. This shape now is what is called a cyclic collateral. So if one of it is not touching the circumference, it is not called a cyclic collateral. Now, this particular theorem now states that, let's label this as A, B, C, D. The opposite angle of a cyclic collateral are supplementary. That is, they are equal, they add up to 180 degrees. So what do you mean by opposite angle? This B here is opposite to angle D. So we can say that here, angle B plus angle D is equals to 180 degrees. And when you use 3 letters to label the angle, so it's preferable for us to be using 3 letters in circle. So we can say angle ABC, which means we can put a cap on top of the number in the middle. Angle ABC plus angle ADC, angle ABC plus angle ADC is equals to 180 degrees. So that's what the theorem is saying. In the same way, we have angle A here is opposite to angle C here. So they are also opposite angle of a cyclic chord. So this angle plus this angle as well will give us 180 degrees, which means we can label this as angle BAD is equals to, plus angle BCD. Now, these two angles sum up to 180 degrees. So this theorem is very important as far as circle geometry is concerned. So then there is an extension of this theorem that says that the exterior angle of a cyclic chord is equals to the opposite interior angle. Now, when we have the circle like this, and we have a cyclic quadrilateral, which is a quadrilateral inscribed in the circle, and the side is extended, this angle here is the exterior angle. Then what the theorem is saying is that this is equals to the opposite interior angle. Now, that theorem is, direct. We don't need to waste time, because if we are looking for this angle, it will definitely be equals to the opposite interior angle. Why? Because sum of angle on a straight line is 180. So this angle inside here, if this, let's label this angle as A, this as B, and this as C. So the theorem says that angle C is equals to angle A. That's exterior angle is equals to the opposite interior angle. The reason being that we have A plus B equals to 180 degrees. That's opposite angle of a cyclic quadrilateral, add up to 180 degrees. And also, we have B plus C also equals to 180 degrees. This is sum of angle on a straight line. Then, since the two results here are the same, and B here, we maintain B here, B is still serving as B here. It means that instead of writing A, I can equally write C. So far, these two add up to 180. These two add up to 180. B is B, B is B. So it means here, this A and C here are the same. So therefore, that's why we say A now is equals to C, which is exterior angle of a cyclic chord is equals to the opposite interior angle. Now, any of the side might be extended, even if it is this side that is extended. This exterior angle, call it angle D now, will be equals to this opposite interior angle, which is angle E. Whichever side is extended, if it is this side that is extended, this angle here will be equals to this angle here. So that is how this theorem goes. So with the understanding of this theorem, you'll be able to solve some given riders, that is, some given problems. When we are given problem on circle, we combine the lines together in such a way that we might apply 2, 3, 4 theorems in one question. So when we look at the question, we'll be able to see any theorem that's applicable first, we apply it. Then with that, we will seeing the next one and be putting it on each other until we arrive at the final answer. Then let's look at one question here to show this particular problem on what we have. Okay. So we are given this circle labeled as, we have a cyclic quadrilateral here, which is in this format. And we are given the center hole, and this line joined to this place joined to this. So this angle here is given as y, and this angle here is given as 129 degrees. And from here, we are asked to find the value of y. Of course, this is labeled as A, B, C, D. Now, when we look at this shape, we discover that A, B, C, D is a cyclic quadrilateral. That is a quadrilateral inscribed in a circle. So we can say that angle B plus angle D here, we add up to 180 degrees, which implies that here I can say 129 degrees plus, if I use three letters here, that's angle ADC. This angle marked here is equals to 180 degrees. You put the reason in front. Opposite angle of a cyclic quadrilateral. So it's very important we put this. Then that means angle ADC now will be equals to 180 degrees minus 129 degrees. When we take 129 here, we come minus. So this gives us 51 degrees, which implies here that this angle here is 51 degrees. Then to get y, look at this shape. This angle, this form angle at the center here. When we consider this arc AC, this arc AC now subtend angle at the center and also subtend angle at the circumference. So that means angle here at the center will now be twice times angle at circumference. So therefore we can say y now is equals to 2 times 51 degrees. We give the reason that angle at center is equals to 2 times angle at the circumference. So that's the reason why. Then that means y here is now equals to 102 degrees. So that is just the simple solution to this particular question. So it is easier to solve when we know the theorem that goes along with this particular question. So it's important to study those theorems in order to be able to solve questions. Now let's look at another question from here. We're also given a circle. And from here, we have this shape. We have a circle. Also, center hole with a line passing through this center hole this way. Then we are given a line here this way and form another angle at the circumference here. Then from here, this line is drawn towards here and joined together with this, and it's used to form an angle with this. So here is labeled as A, B, C, then we have D, E here. So don't forget this center hole of the circle. And we are given this angle to be 127 degrees. That is, from here, we are asked to find angle ACE. So we are finding the value of angle ACE here. So that's what we are finding. So it's important to note from what we are given that once we have the center and we have a diameter, that means this diameter now divide this circle into two. That's semicircle. An angle formed by the diameter is same thing as angle in a semicircle, which is 90. So the whole of this angle here by this diameter, this angle is expected to be 90 degrees. So that means the whole of angle CDE, angle CDE, angle formed by this diameter, angle CDE is equals to 90 degrees. So it's important to note that. Then, what is important again from here is that we have a shape like a cyclic quadrilateral. From here, we see A, B, C, D is a cyclic chord, and B here is opposite to D here, which is angle ADC. So I can say that angle ADC there now will now be equals to 180 degrees minus 127 degrees, because these two now must add up to 180 degrees, which give us 53 degrees. So that is that. Then, if this angle is 53 degrees, easily from here, we can get this angle here, because everything here we said is 90 degrees. So that means angle ADE, this angle ADE here now, the one marked here, ADE, is now equals to 90 minus 53. That's because everything here is adding up to 90 degrees, which means here this gives us 37 degrees. So now if this angle is 37 degrees, and don't forget what you are finding here, which is angle AC. Now, where is angle AC? This here is angle ACE. So we mark this angle in between that line of AC and CE. That's ACE. Now, when you look at that as well, very well, you discover that this arc AE subtend this angle C here and this angle D here in the same segment. So it's something like this when you look at it very well. So we have it this way. It's because we are not having a chord there. It might be somehow, but when you look at it, assuming this is just a chord here, the same way we look at angle in same segment. So this chord now is representing an arc, which is A, instead of a chord. So this angle here and this angle here, they form angle in the same segment. So this is 37, this is also 37 here. So therefore, we can conclude that angle ACE that we are finding is also equal to 37 degrees, which is angle in the same segment. So that's the solution to this given problem. We are able to arrive here because of what we know about the theorem, which is circle theorem. So you have been watching us live at MasterTMathsclass. Don't forget to give us your support by subscribing. Also give a thumbs up, share this video so that when we meet next class, you won't miss this class. And thank you. See you next class and bye for now.